So we're, oops, sorry, it went ahead. Okay, there's an animation which, okay, it started. So we're fairly confident now that there's a supermassive black hole in the center of every galaxy. The most compelling evidence comes from our own galaxy. And what the animation was showing is the orbits of stars around a very massive dark objects in the center of the Milky Way. We call Sagittarius a star, and this is what we think is the supermassive black hole, our own supermassive black hole. So for reasons we don't fully understand yet, a small fraction of these galaxies and the supermassive black holes launch collimated, often highly relativistic streams of plasma that we call jet, that are powerful enough to punch through an entire galaxy and into the intergalactic medium. So here's what kind of typical radio galaxies, or as we call them, this is for historical reasons, because they were first detected in radio back in the 60s. And this is kind of what most of them look like. What you see here is a bright spot in the center, and this is where the supermassive black hole is, and what we call the AGN, which starts for active galactic nuclei. And then the thin lines that are coming out of it to the left and right, this is what we call jets. And at the end, you see these big bubbles that we call radio lobes, and this is basically where the jet terminates and started mixing with the intergalactic medium, and it's forming shocks. So if you kind of focus on the AGN, this is what it would look like roughly. The bright spot you see there is what we call the core of the jet, and what's coming out towards the right, that's the main jet. There should be an identical jet on the other side. This is what you see, but of course it's a little bit dimmer in this case. And somewhere between the jet and the counterjet, there should be the supermassive black hole that is powering both of them. So radio galaxies are nice, and they make very pretty images, but I'm mostly interested in a subset of the radio galaxies that we call blazars. And these are sources where the jet is oriented towards a line of sight. And that actually is giving them very interesting and very peculiar properties that I'm going to discuss shortly. So this is how a blazar would look like. Of course, you can now tell that we've lost the beautiful two-jet structure, and we just see a bright spot that we still call the core of the jet, although it doesn't necessarily correspond to what we call the core in radio galaxies. And then we get a little bit of the main jet, because of course these are not oriented exactly at 0 degrees to the line of sight. They're typically a few degrees kind of off axis. So the way that we study these objects, mostly since we cannot resolve anything anymore, is to look at the multi-wavelength emission that they have, and recently the multi-messenger emission, and try to figure out what is happening kind of internally. And I'm showing you here kind of one model that exists to do that. Of course, this is not the only model, but I would say it's the most popular kind of the models out there. So what you see here is here, I hope you can see my cursor. This is where the supermassive black hole is. It has an accretion disk, and the accretion disk is constantly feeding it with gas. And then the jet is launched, and it propagates outwards, going through what we call the broadline region, which is what you see here. And these are just clouds of gas that are orbiting the black hole. And this is where the emission lines we see in the optical are coming from. And then the jet moves outward, and it gets accelerated, it's collimated, and then it goes to a place we call the millimeter wave core. And this is thought to be either a standing shock or the first collimation shock of the flow. But in any case, this is where we expect to have a lot of particle acceleration and high energy emission. And then after it passes that millimeter wave core, then we enter a region where it's dominated more and more by radio. So if you look at M87, which is coincidentally, the source that gave us the image of the black hole. M87 is not really a blazar, but it's not really a radio galaxy either. It's kind of something in between. We often call those type of sources misaligned AGN. And you can see here in the images I have in radio, optical, and X-rays, that kind of the emission profile is a little bit more complicated than the simplistic kind of picture there, but a lot of the structure is present. And in fact, there was a paper a few years ago that studied how the profile of the jet evolves as a function of distance from the black hole. And what they found is that you tend to have a parabolic jet in the inner region. And this is according to our IMHD simulation. Parabolic jets favor acceleration until it reaches the HST1 complex, which is also thought to be a recollimation shock. And that also happens to be at the Bondi radius, which is where the sphere of influence of the black hole ends. Whether there is a connection is still really unclear, but the result was that after that that standing of the Bondi radius, the jet transitioned to a conical geometry. And again, conical jets do not favor acceleration. So this kind of matches what we had in mind from the model that I just showed you. And in fact, very recently, Yuri had a paper where they studied nearby radio galaxies. This is just one of the examples from that paper. And they also find this transition between parabolic and conical geometry. So that seems to be kind of a more universal feature in these jets. So my talk will focus on kind of this part of the emission. This is we're now looking at parsec scales away from the black hole. And this is where we think mostly radio is coming from. So typically radio is thought to be kind of the less variable of the wavelength, especially if you compare it to optical and gamma rays. But as you can see in this example, this is from the Owens Valley Radio Observatory. Radio can be fairly variable itself. So of course you have to wonder, where does this variability, where is that variability coming from? So you might consider that you have an accretion disk, and the accretion disk has gross instabilities. There are some changes in the mass accretion rate, and everything that kind of changes in the accretion disk translates or better propagates in the jet through some disk-jet connection, and that will give you the variability that you see. In this case, we call that we have kind of multiplicative processes, and you expect to then, if you look at the distribution of the fluxes that you get from your source, those should be close to a log normal distribution. And this is, although this has been kind of disputed lately, but this is kind of the general picture that we have also from the X-rays and non-jetted AGN. You could also have a scenario where you have a combination of standing and moving shocks. Those will have, you will have some underlying variability, and on top of that, you have flaring episode, which is fairly close to what we typically observe in blazars. And then you can also have scenarios where the jet is wobbling around, is moving and changing the orientation to the line of sight. This could be due to a number of different effects, from binary black holes, from instabilities in the jet, from just bends due to environmental reasons. But basically, the changes that we see in the light curves do not come from some particle acceleration, but they're just simply an effect of the orientation changing. So the most kind of common model that we use to describe when we want to have a distribution of the fluxes, or the flux densities that we get from a source, is of course a Gaussian distribution, which is the easiest one. And especially when you're looking, there's a lot of literature out there when they're looking at significance level for correlation or periods or whatever, and they're when they're trying to simulate light curves to evaluate the significance, the most common methods have the underlying assumption that the distribution that your source is sending in fluxes is Gaussian. So then if you assume that the true distribution of your source is in fact Gaussian distributed, you're not going to measure exactly what the source is sending your way, but of course you have some observational uncertainty, but you can take that kind of into account and write down a simple likelihood that will allow you to recover your kind of the intrinsic distribution that your source is sending. So here's an example of another source from the Owens Valley Radio Observatory. It's a very famous one, so it's called VLAC. And on the left, you see kind of the light curve of the source, and the right is that flux density distribution I've been mentioning.
You just connect points here, right, Yanis? You don't model it. It's just connecting point on the left-hand side.
Oh yeah. This is just the plotting.
Of
course, there's no model for that. So as you can see on the right, this is not really doesn't really look kind of Gaussian. And in fact, if you try to fit the model I showed you earlier, this is what you get, which still captures the median value of the distribution, but of course it's not a good model for the underlying variability. So when you try to use that to either generate light curves or do any statistical analysis, things are not going to end well. So we thought we might be able to do a little bit better, and the next logical step would just be to add an extra Gaussian, so have two Gaussians instead of one, or as statisticians like to call it, a Gaussian mixture model. So I mean, the premise is the same. You just have your source sending you fluxes from a Gaussian mixture model, and then you have to take into account the observational uncertainties. You have to write a slightly uglier light code, but nothing too fancy. But you can get a much better fit to the data, and you have a much better description of the underlying variability. So you might be thinking, what is the physical interpretation of this? So what we had in mind at the time is that the source undergoes changes in the activity state. So basically, the first peak you see here, this kind of describe the underlying quiescent or steady state emission, if you will. And then on top of that, you have flaring episodes that will create kind of the second flare. And if you really put things together, this would be consistent with having standing shocks or one standing shock, the core doing what core or what standing shocks do, just fluctuate randomly about some value, which will be the first peak, and then you have the emergence of new shocks, or you have shock-shock interactions that will create the second peak. And this is in fact, as I've already mentioned, what we see through VLBI happening with jet components moving around, and they're not causing only variability in radio, but we see a whole mess of interesting phenomena like gamma ray flares or rotations of the UPA and a lot of other stuff. So recently I looked at this particular source for a different project, but it was kind of relevant to mention here. This is another famous source, and I'm showing you here the light curve from the University of Michigan, which started observing these sources back in the 70s and continued until around 2012. This shown in black, and then in red is the Owens Valley light curve, which started around 2008, and it's still going on.
Yanis?
Yes?
Allow me to interrupt you and to ask sort of, non purely scientific question, but could you please comment on the amplitude calibration comparison between Michigan and Owens Valley. Do you agree very well?
In the common region, yes, they seem to be fairly consistent. At least in this example, because I've checked that.
Very good. Yeah. So sorry, Yanis, it looks very good. So I wonder, what is the is it within 1%, 2%? If you have actually taken a close look at it. Sorry.
I did not look that closely. I just looked by eye and saw that the points that were at the same dates, they matched pretty well. But that should be, if you're interested, that should be fairly easy to look into. Okay, so I guess I can move on. So what you see here is that the source was very, well, it was still active in a sense. I mean, it's still fluctuating for kind of a Jansky back in the 80s and 90s, but it was at a very kind of different level than what we see today. So in this part is, you would characterize this as a kind of a quiescent level, and then suddenly, in the 90s, it started for some reason to flare up and have this gigantic 3 Jansky flares, and it actually has continued to do so all the way up to today. So if you look at just the University of Michigan data, this is the black curve. Again, you will find this kind of weird shaped Gaussian with quiescent state or kind of a low amplitude or state, and then a tail that kind of goes out to higher fluxes. If you look just the over data, then that quiescent peak has actually moved much higher, but it's still, you kind of still see that this is not consistent with just a single Gaussian model. And then, of course, the true picture is when you join everything together, and then which is the green curve, and it becomes absolutely clear, what the source is doing kind of overall. And this is over 40 years of data. So it really kind of highlights the importance of really long-term monitoring of the sources in order to kind of understand really what they're up to. And unfortunately, the University of Michigan stopped observing after roughly kind of 40 years. So I'm really hoping that programs like overall or the Ratan 600 will continue to do so for many years to come. So before I move on, are there any questions on this part of the talk?
No, Yanis, everything is actually crystal clear. So I usually ask more questions, but you explain everything very truly in all the details. Thank you.
I hope I'm on time.
We still have Zhenya. Zhenya, go on.
I have a small question. I don't know whether you're going to continue in the same task, but I wonder, so when you plot these levels that you measure this using like medians of these 2 Gaussians and plot on the same light curve. And I mean, what I usually think that the activity coincides with the rise of the flare. So it was shown that the blob, there is some blob emerged from the core during the, not the maximum, but somewhere before the maximum. Can you comment on this?
So the modeling here does not know anything about time. This is so this is maybe more related to what's coming next. But here we're just looking at, so if you look at kind of this light curve, it will tell you, you can see the cursor, that kind of this part would be the quiescent level that is fluctuating about some value, and then the second peak would be somewhere here, and it will have a range. Oh, sorry, have a range kind of this. So it's not really, yeah, it doesn't really know anything about time, unfortunately.
Okay, thanks.
One more question. Why don't you fit it with a log normal distribution? Because obviously a Gaussian is working not very good at the zero level.
So there are two reasons for that. One of them is practical. So we tried the double Gaussian because log normal is not, you cannot get an analytic solution for the likelihood, which complicates things a lot. The second reason is this example is kind of a mild case. We have a lot of examples in the over data that you clearly see two separate peaks, which are, obviously cannot be described by a log normal distribution. That was the kind of the main motivation for that.
Or maybe sum of two log normal distributions.
Well, I mean, there is always you can always do the trick of doing a Gaussian distribution, but with log data.
Sure, yes.
But I have not tried that in that data set but that would be something maybe interesting to look into.
Okay, thank you.
Any more questions? Okay, then I'll move on to something else that we can learn from radio variability, which is I think quite important, and it's actually something that is kind of limited to radio variability, and that is that we can constrain the orientation of the jet and the velocity, which we cannot do with any other method. Actually, we cannot do it separately unless we have VLBI information, but what we can do with just the radio variability is look at the combined effect, which is something we call the Doppler factor. And this is what I show here with this delta parameter. So the basic premise of this is that because of synchrotron physics, there is a maximum brightness temperature that the sources can achieve. Some consider that to be what we call the inverse Compton catastrophe, and that's around 10 to the 12 Kelvin. Others think that this is slightly lower in a state that they call equipartition, which is basically where the energy density of the magnetic field and the radiating particles is roughly equal. But it doesn't really matter. If you know that value of the intrinsic brightness temperature, any excess you measure above that, it has to be attributed to those relativistic effects. And then you have VLBI, then you just a simple ratio of the two, and that will give you the Doppler factor. If you have a light curve, then you can fit the flares that you see, and then you can relate the rise time of the flare to with some causality argument, the size of the emission region, and that will give you a slight, different ratio, but it's still pretty straightforward to estimate that. So, until even recently in 2009, we just had Doppler factors for, a few tens of sources. So we thought it would be a good opportunity to try and do something better. And at the time, we had a very interesting data set on our hands. It was from the Max Planck Institute for Radio Astronomy and the F-gamma team, which observed about 60 blazars in 10 different frequencies from 2.6 to roughly 140 gigahertz. And they were doing it with a cadence of once a month at best to more typically once every 2 months. And I'm showing you here an example of 3C454.3. I really kind of like this source because it shows very clearly and very strongly spectral variations. This is not typical. Of course, most sources show just slight shifts between frequencies, and a lot of them actually show quite almost achromatic variability. So one of the problems that we're facing when you're trying to do this business of estimating, the rise time of flares is the fact that in radio we have a lot of overlap between different flares, and that of course can cause some bias in your estimation of the Doppler factor. So we wanted to kind of incorporate all the multi-wavelength information that we have from the F gamma data set to try and account for that effect. And one reason is that there is a relation between the time scales and the observing frequencies. For lower frequencies, the flares tend to evolve at a slower rate compared to the high energy. So we wanted to try and use the high frequency data that we have and trying to disentangle flares at the low frequencies. And of course, in order to do that, you need to have a model for the flares in your light curve. And we did that by just finding the peaks that we saw in each light curve. And then you make a copy of the light curve for each peak, rescale everything to some flux level. We just chose the highest flux that we had in the light curve. And then you just stack all the light curves together. And that will create this figure you see here. And then the area that is kind of shaped out from all those flares that you've stacked, which is shown in red, gives you a basic model for the flares in that particular frequency. And of course, you have to do this for all different frequencies in its source. But then if you have a model for all the flares and you know what is the shift between the two frequencies, then you can use kind of a method similar to clean, which you're using in the LBI, where you subtract a light curve, subtract a flare from the light curve, and then look at your residuals, and then so you subtract more flares or less flares, and you try to basically end up with the residuals of your light curve to be noise, basically. So here's two examples.
Yanis, sorry, let me interrupt you if it's okay. So that could you please go back to the previous slide, or let's say previous picture? Yes, thank you. So two questions here. Number one, how do you determine the model with the errors of the model? So is it simply the I don't know, scatter of these stacked data points together? And immediately the question number two, it might be that I have just missed it. So you stack on which point? So how do you stack them? How do you align them? Thank you.
So this is, you basically align them with the highest flare. So you just find what's the peak of the highest.
You align on the peak. You align on the peak which is modeled, or you simply align it on the highest data point.
The highest data point, basically, and then the error bars you see there are just you're trying to fit a line underneath that curve, and that kind of gives you some uncertainty where
so the errors are from residuals.
It's from, well, yeah, in that sense, yes, it's from the fitting, which is.
Thank you. It is a little bit strange, right? So you think that you are always extremely lucky getting the peak of the flare in your observation, which is certainly not the case, right?
Yes. This is not the only problem with this exercise.
Sure, it is not the only one. Okay.
Okay, thank you. I will go to more problems in a minute. So yeah, so these are just a few examples, or two examples, where black is the data point and then red is the model for the light curve having subtracted the background. So as you can see, given the data, we're able to capture the variability that we see fairly well. But as Yuri mentioned, there is a big issue here with the cadence of the observations that we realized fairly quickly. And once every 2 months is certainly not enough to resolve all the flares. And this came, what we were finding basically is that the high frequencies we're really kind of underestimating the Doppler factor compared to the low frequencies, which seemed to be a systematic trend that was kind of worrying us. So at the end, we reported the highest Doppler factor that we found in each light curve, and that typically was from the low frequencies. So we did manage to add 20 any more estimates of Doppler factors in the literature, which at the time it was, a 25% or 30% increase. So there was not nothing, but clearly we needed to do better. And we needed to have a survey that would have, a large enough sample that would also allow us to do statistics. And it had to be with a very high cadence that will then alleviate all these problems with cadence. So we were lucky enough that survey actually existed from the Owens Valley Radio Observatory. Was monitoring roughly 2,000 blazars, starting in 2008, where the Fermi Gamma Ray Space Telescope was launched, and it continued until end of 2020. We've now transitioned into a different mode where we observe the sources less frequently, but we observe now up to 5,500 sources. So it's a even much larger sample. But in this particular case, the cadence was every 3 days, which at the time we were hoping that is enough, but we made sure that this is actually plenty to resolve all the flares in the light curves. And you can see here a few examples of how beautiful, fairly uniformly sampled and high cadence light curve look like. Of course, you might notice that there's a lot of kind of diversity in the variability patterns. So I had to kind of go through all these 2,000 sources and basically find the ones that had, at least a few years of observations and that showed some flaring activity. And that,
Yanis?
Yes.
There are two minor pieces of information which you didn't say out loud, and they might be interested for many of us. So first of all, coming from the end, you said that when you have originally, the group of the Owens Valley monitoring has originally planned to have one observation every 3 days, and you thought that it is enough for any kind of flare. Apparently, we expect you to comment. Was it enough? Was it a correct expectation?
I can tell you that for the vast majority of sources, it was enough. But we are suspecting that there are a few sources that we're actually undersampling.
Can you comment on physics? So you think that you undersample physics of the source or physics of interstellar scattering?
Oh, there was a study on the interstellar scattering.
Sure, it was. And yes, I don't ask you right now to present to us another colloquium on another subject. Still, you said, it was not me, you said that you had a few sources for which this once in 3 days was not enough. So still, you are referring to the physics of jets or physics of the interstellar scattering?
I'm not entirely certain on that. I cannot answer on top of my head.
That's good enough.
There was a study on the interstellar scattering on the oversample, but I don't remember because I was not involved in it, so I don't know. I don't remember exactly what was the conclusions and if what they found was related to the sources I have in mind right now.
Yeah, we know at least for the very well. Yeah. Sorry, I want to say that we know this paper very well, and for some events, once in 3 days is enough. For some, I mean, scattering wise, it's not enough. So, but at least I understand what we are talking about right now. And the second, very quickly, I know the answer, but I think that everyone is interested. The new program, which is monitoring up to 5,500 HGN. What is the cadence of this one? Thank you.
So, sorry, which program? The
new
program.
one,
Okay.
yes, 5,500.
Yes, I didn't hear the new. So that is going to be every 10 days, roughly.
Thanks.
I mean, you always, this is the nominal cadence, of course. Even the 3-day cadence, it was not always exactly 3 days. You have weather, you have all sorts of things, happening, right?
Sure.
But at least the nominal cadence of the new program is going to be 10 days.
Okay.
So going back to the original sample, it was 1,029 sources. You can see the demographics there, which would have been kind of a heroic effort to model each source individually. It would have taken forever, for sure. And most importantly, every time you make a choice, which flare to fit and which not to fit, you're introducing a bias. So we wanted to have to do this in a timely manner that was as human-free as possible. So we chose a code in order to do that, which is a code that's called Magnetron. This is a Bayesian hierarchical model that's implemented in Python, which makes it very, very convenient to use. And what Magnetron is doing, it has a stochastic background that captures all the low amplitude variability. And then on top of that background, it superimposes flares with an exponential rise and exponential decay profile. Now, this time we don't have a fixed shape for the flares. Each flare is different. It could be pretty much any shape. But what is more important with Magnetron is that we no longer get a best fit model, but we get a posterior distribution of possible flare models and backgrounds that describe the data, but take into account all the uncertainty we have in the number of flares that you have in the light curve, how strong is the stochastic variability, the observational uncertainty. And that kind of posterior distribution actually allow us to have some meaningful uncertainties for the parameters we're interested in. I'm just showing some examples here of Magnetron's handiwork. Magnetron was initially made for magnetar flares. This is partly where the name comes from. So we had to make adjustments in order to make it kind of suitable for blazars, but you can find it in that GitHub page. So for every of these models that we have from the posterior distribution for each source, we can estimate what is kind of the highest brightness temperature that we see. And then we can make a distribution of that and estimate median and confidence intervals. And this is what you see, a few examples on the left. And then if you just do the distribution for all 1,000 sources together, this is what you see in the right. And what is, of course, interesting here is if you split your sample, whether the sources have been detected by Fermi. So if they're making gamma rays or not, we found that the brightness temperature for the gamma ray sources is systematically higher than that of the gamma ray quiet. This is, of course, something that we kind of knew already from the Mojave survey, but it's good to kind of confirm it using an order of magnitude more sources now. So if you have that distribution of brightness temperatures, then you can use population models that I had cooked up when I was still a PhD student and use them to constrain what is that intrinsic brightness temperature you expect. And we also we assume that there is some more underlying model for that intrinsic brightness temperature, which conveniently is Gaussian with a mean of 2.78 times 10 to the 11 and a spread of about 26%, which is absolutely fantastic because it's comfortably sitting just above the lower limit we had from VLBI observations, so we don't have a tension there, but it's also kind of far enough below the inverse Compton catastrophe limit, which tells us that there has to be some truth to this equipartition argument and the balance between the energy density of the magnetic field and the radiating particles. Of course, if you have that estimate now, you can go back and estimate Doppler factors.
Sorry, Yanis, I truly have to interrupt you right now.
Sure, go ahead.
So first of all, 3 times 10 to the 11 is not much less than 10 to the 12K. It is quite comparable. And second, the inverse Compton brightness temperature, if you are talking about the intrinsic one, is not 10 to the 12. It is much closer to 10 to the 11 and a half, according even to the paper you referred to in this paper. So actually, the intrinsic brightness temperature, which you claim is your best fit model, right, is very close to inverse Compton brightness temperature. Okay. I mean, it's not a question, it is a statement. If you disagree with that, please tell so.
Well, I cannot really disagree in the sense that, I mean, it depends what assumptions you make. You will end up with a slightly different different estimate for the inverse Compton.
That's correct. So it depends on your geometry and many other things, but your number, whatever assumption you take, your number is not much less than inverse Compton brightness temperature. It is close to, it's actually very close to, with a high, as we call it, at least here. Okay, as I like to call it, with a high astronomical precision.
Well, with high astronomical
it is within an
precision,
order of magnitude, yes. But well, if you consider that to be 5 times 10 to the 11, then I think I'm within 1 sigma or 2 sigma.
Correct,
So,
within 1 sigma, yeah.
Yeah, in that sense, yes, it's consistent. But I'm not arguing in favor of one or the other. I'm arguing that you should be using my value.
Oh yeah,
so,
that now the question. So please comment. How much do you believe your value, and it's wonderful that you use this particular wording, your value is dependent on the model assumptions? Thank you.
Okay, so of course it's model dependent. There is no basically all comes from the population models that I trust them. I would say, I mean, I wouldn't say completely, but so far all the the predictions we've made with the models and all the checks we've done have come true. And of course these models only depend on very robust observables. We optimize them based on the redshift and the apparent velocity of the source. We have no flux whatsoever. We have, of course, there are assumptions that, for example, there is a Lorentz factor distribution that follows a power law, which seems to be the most likely case. There is a luminosity function that also has to be a power law. This, we can dispute on these details, but so far, every check we've made and every test we've done seems to be okay.
Yeah, I think that we should discuss this population modeling, because this is important by the end of your talk. But if you can shortly say right now, which model assumption you believe? Okay, I don't want to say drives this value, but is the most critical one. Okay, and then we go on. Thank you.
Oh, that's a tough one. I would say the limits that we have on the assumed these power law distributions would have an effect on the index when we're optimizing them. So I would consider that to be kind of important. We have assumed some cosmological evolution, but then there was other works from Lister et al. That used different cosmological evolution, and we came to consistent results. So I'm not worried about that.
Yes, we are consistent there. Yeah, that's true. Mm-hmm.
So yeah, I would be just worried about those ranges, which were, they were motivated by the data, but in some sense, also a little bit arbitrary. But that would be my main concern.
There's a question: what's the physical reason to believe that brightness temperature should be intrinsically just single value, not a distributed value, also, right?
I mean, that's the main. So we actually tested that. So when we assume that there's a model for the underlying for the intrinsic brightness, we tested. Had uniform delta function, Gaussian, log normal, and exponential, I think. And then we're coming up with, so we did the best fit model, and we model selected between all 5 of them. And the Gaussian was the best, let's say the preferred model for the data.
This is intrinsic brightness temperature for the flaring state, okay? So for the peak of
yes,
the flare,
this is for flares. This comes from the flares. But definitely delta function was not preferred over Gaussian. So it has some spread, at least over the population of the sources that we're looking at.
Just out of curiosity, if you assume still a delta function, what kind of brightness temperature you would get from your model?
It was similar.
Similar.
It was similar. I don't remember exactly if it was higher, but of course, this, I mean, you expect, if it wasn't similar, I would have been worried. But I don't remember if it was lower or higher. But it was in, you know, in close in that range.
Well, it should be, of course, but it should be like a factor of something different from what you have.
Yeah, I actually would expect also this plus minus 26%. So the plus and minus should be different numbers, right? And this would hint where the delta function moves.
Yeah, I did not check an asymmetric distribution.
It should be asymmetric, and Yanis, it should be.
I don't argue.
Yeah. Okay.
So, okay. So yeah, I was saying you can estimate now Doppler factors for individual sources. And again, this is a whole, what the distribution of all the sample is looking like. And of course, the two interesting things here is one, the typical value that people have been assuming when they don't know anything is around 10 for the Doppler factor. This is close to the median that we find, which is around 15, you know, depending on how you split your sample. But we do find Doppler factors in, you know, in excess of that, close to, you know, 40 and 50. Of course, these are, you know, much fewer in number, but you know, at least they still exist. And the second interesting finding that we had was that we no longer find a difference between BLX sources and flat spectrum radio quasars. And at least that was kind of the main idea or the main, say, the consensus in the literature, that flat spectrum radio quasars were more beam sources. And one of the reasons we think that is because we find that the flares in BLX tend to happen in slightly shorter timescales. So then you can imagine programs like F-gamma, which have a, you know, monthly cadence, would have captured this long kind of rise flares from FSRQs, but would miss a lot of the shorter timescale BLX flares. So that kind of gave this asymmetry, but we don't really find a difference anymore. So we have a tool now to, you know, to work with light curves from radio. We have a kind of an updated estimate, hopefully the correct estimate from our discussion of the intrinsic brightness temperature. So we really wanted to kind of use it to learn something more about the, you know, the jet structure and the internal processes. And we thought we'll start with try to see if we can find evidence for acceleration or jet bending in the sources. So here's just an example of a kind of a combined data set that we managed to get for about 60 sources. This shows data from the Michigan Observatory in 3 different frequencies and the Metsähovi Observatory in Finland in 22 and 37. This covers kind of a time span of over 20 years, or at least kind of the common time span is about 20 years. So the idea here is that because of secondary self-absorption, different frequencies look at different locations along the jet. So if you manage to quantify the Doppler factor for each frequency, you can see how that evolves as the distance from your black hole. And of course, in this case, we had a much shorter frequency range than we had with gamma, but now the cadence for this data set is much better, is from a few days to a couple of weeks at worst. So then again, we estimated Doppler factors for all the frequencies and tried to quantify statistically if there is a persistent trend for the Doppler factor. And I'm showing here a couple of examples. So the black points you see are the estimates we have from the University of Michigan and Metsähovi data. The red dashed line is the fit that we get just the black points. And then for consistency checks, we use data from ALMA, KARMA, and SMA. That was 100, 230, and 340 gigahertz roughly, just to check, how the trends, if the trend continues or not. So this is from a paper that would be submitted actually a few days ago. So if you have comments, that would be very, very helpful. So the majority of the 60 sources, of about 42, if I'm not mistaken, are very similar to panel D. This is 3454.3, where we did not find any statistically significant change of the Doppler factor across frequencies. And that kind of points to that we're looking at conical, jets that are not, that are straight and non-accelerating. But we also had 17 sources that showed a different behavior, 16 of which showed the behavior that you see in panels A and B, which is basically the Doppler factor growing towards lower frequencies. So basically either the jets are accelerating or they're bending towards our line of sight. So we looked into the VLBI properties of the jets and tried to figure out, which is which. And here you see a comparison of the position angle of the jets at 43 and 15 gigahertz. Most of the sources that you see are, fairly consistent with each other, but there is one example, which is, the position angles is very different. This is 0420 minus 014, and this is the source that you see in panel B, actually. So that change in the position angle between the frequencies is telling us that the jet is likely bent, and the trend that we find from the 4 to 37 gigahertz seems to continue all the way down to almost 340, and that tells us that there has to be some continuous bending of the jet across all that frequency range. One out of the 17 sources is the one in panel C. This is 3C279. And that's the only one that showed the exactly opposite behavior. So the Doppler factor is decreasing towards lower frequencies, which either tells us, again, that this is decelerating or is moving away from our line of sight. But I don't remember which one is which, but one of the green points is 3C279. So the position angle is not different. So this is most likely a deceleration, the source is decelerating. But what is more interesting is that when you look at the high frequencies, you see that the source is accelerating. So that was peculiar, of course, but if you really think about it, if you go back to this transition jet model, then it could be that the inner jet is in a parabolic shape, so it's accelerating, and then after it transitions to conical at around 100 gigahertz, then it kind of loses steam and starts kind of decelerating. This was our most, let's say, our preferred interpretation, although I noticed a paper a few weeks ago from the EHT collaboration where when they're looking at the 200, close to 230 gigahertz, they found that the evidence of the jet being slightly bent, which then you can interpret this that the inner jet, there is this kind of bend that leads to an increase in the Doppler factor. And then when you go to the gigahertz range where the jet is no longer bending, you see this deceleration effect. So, still uncertain, but certainly quite interesting. So just to summarize, I didn't have to convince you that astrophysical jets are exciting laboratories. I just want to emphasize it. And radio variability is a very important probe of these processes, and we're really learning a lot. Of course, we still have a lot of open questions, and I would say the most hot ones now are, of course, the connection to high energies, and especially the connection to the multi-messenger emission in terms of neutrino, which is, of course, something that you guys here are leading. And there's also a lot of discussion recently on periodic jets, which could also be, evidence of binary black holes, and that ties into the second branch of the multi-messenger emission through gravitational waves. This is something that we're actually working on with people from over now. So I don't want to, really want to say much, but we're finding basically what people have already been finding, that these are, if they exist, these are not very common. But we'll see shortly.